Henderson equation? So if you see, the pH of an acid buffer can be calculated from the dissociation constant Ka of the weak acid and the concentrations of the acid and the salt used. So the dissociation expression of the weak acid HA may be represented as HA, that is equals to H plus A minus. Ka will be equal to H plus into A minus divided by HA. So here is the person Henderson. So he derived this equation, that is dissociation expression. So this H plus, that is equals to HA into Ka divided by A minus. So the weak acid is only slightly dissociated and its dissociation is further depressed by the addition of the salt Na plus A minus, which provides A minus ions, that is the indication of common ion effect. As a result, the equilibrium concentration of the unionized acid is nearly equal to the initial concentration of the acid. So the equilibrium concentration A minus is prepared, that is presumed to be equal to the initial concentration of the salt added. Since it is completely dissociated, thus we can write the equation as this equation can be written as this is the first equation. This can be written as H plus, that is equals to Ka into acid divided by salt, where acid is the initial concentration of the added acid and this salt is the salt that has been used. So taking negative logs on both sides of the equation number 2, we have minus log H plus, which is equals to minus log Ka into minus log acid divided by salt, mentioned as equation number 3. But minus log H plus is equal to pH and minus log Ka is equal to pKa. Thus, from equation number 3, we define pH is equal to pKa minus log acid by salt, that is equals to pKa plus log of acid divided by, it's not acid, salt divided by acid. So on further, hence we got pH is equal to pKa plus log of salt divided by acid. This relationship is called the Henderson-Hasselbalch equation or simply Henderson equation. In a similar way, Henderson-Hasselbalch equation for a basic buffer can be derived. This can be stated as POH, that is equals to pKb plus log of salt divided by acid. So let us now see about the Henderson equation in terms of significance of the Henderson-Hasselbalch equation with its help. So if you see, the pH of the buffer solution considering can be calculated from the initial concentrations of the weak acid and the salt provided Ka is given as pH, that is equal to pKa plus log salt by acid. However, the Henderson-Hasselbalch equation for a basic buffer will give POH and its pH can be calculated as 4, it is not 4, it's 14 minus POH. So POH, that is equals to pKb plus log salt divided by acid. So the dissociation constant of a weak acid or a weak base can be determined by measuring the pH of the buffer solution containing equimolar concentration of acid or base and the salt. So pH will be equal to pKa plus log salt by acid and POH will be equal to pKb plus log salt by acid. Since salt is equal to acid, log of salt by acid will be equal to log 1, that is equal to 0. So pKa will be equal to pH and pKb is equal to POH. So the measured pH therefore gives the value of pKa of the weak acid. Likewise, we can find the pKb of the weak base by determining the POH of equimolar base buffer, that is basic buffer. So a buffer solution of desired pH can be prepared by adjusting the concentrations of the salt and the acid added for the buffer. It is noteworthy that the buffer solutions are most effective when the concentrations of the weak acid and the salt are about equal. This means the pH is close to the value of pKa of the acid, or as we can say pKb of the base. Thank you for watching this from GTech.